Let's suppose I yell a request and it triggers a response. If that request contains cool, it ventilates cold air. This process is known as compile human readable code. The simplest abstract machine capable of recognizing patterns requires an alphabet, a set of symbols for constructing words. The empty word denoted as E is also present everywhere set theory is about. A star contains all words on alphabet A, including the empty word, and the length of any word is also denoted. So, this notation implies the union among multiple words. A subword of xc will be any string contained. By the way, I'm using Roman literals because they're cool. It can be also natural numbers. Now, a word can be any nonsense combination of characters. The difference against a language relies in the grammar rules that defines such a language. That's what we are interested in this unit. So, a language is a subset of this and also a subset of this. You will hear about these terms often. Because a language is a set of words on A, the set operations like intersection will work the same way. By example, this results on the empty word. By the way, these are nonsense words because we have not seen grammar rules yet. Regular expressions are present on all programming languages. It defines a pattern. So, all sequences of characters containing such a pattern will construct a language. By example, words containing the pattern ISH. It is said those mentioned words are grouped in a regular language generated by a regular expression, which is the most basic grammar structure called regular grammar. For alphabet A, those patterns generate these respective languages. As we saw before, those words are attached to a grammar rules, a regular expression in this case. The best example of these are search engines. You enter a pattern and it will generate a set of words that fits into that specific regular expression for you. A finite state automata should be considered as a machine that receives an input and returns an output. As an example, let's analyze this FSA to detect whether a given string ends in AC. Its components are configured as follows. All input strings must contain only one defined alphabet. The processing states will behave like traffic lights. The initial state, the accepting state, and the transition function where all possible outcomes are defined. By example, for this input starts on Q0 and character A, which gives back Q1, then Q1 and A gives back Q1, and finally Q1 and C results on Q2, ending this processing for this specific string. For this one, Q0 and A results on Q1, then Q1 and B backs to Q0. This given input has not reached Q2, so the result is false. Now, this FSA was designed to analyze such a simple pattern. For real finite state machines, it can contain many states that could be difficult to list like we did before. That's why scientists rely on visual diagrams to design and understand. By example, for this one we begin with Q0 and B, which results on Q0. Then Q0 and B again stays on Q0. Q0 and A will place the state to Q1, where a true results from this processing. Now, when we want to express an idea, we lexically add words that extend and specifically describe a concept. These words emerge following production rules. Verbally, we do this subconsciously. What we are interested in is scientifically expressing a grammar as a group of sets that will produce a sentence representing an idea. For English sentences, we can include a set of vocabulary. In computational models, we will replace this set with an alphabet that allows us to express any word. Then we have terminals and non-terminals, along with production rules. All of these sets depict a grammar. For example, to produce an English sentence, we use a group of non-terminals such as the start symbol, the noun phrase, determiner, adjective, noun, verb phrase, adverb, verb, and the prepositional phrase. These symbols are then replaced by the terminals, which are the words that will be used in the sentence. This whole process is called sentence derivation. For now, we are not interested in the linguistic approaching to grammars, but rather in the abstract model that will be obtained. For example, we have this other grammar and we need to obtain sentences produced by it. Implicitly, the production rules denote non-terminals that exist on the left side of the rule. Similar to the previous example, the capital S represents the start symbol along with capital A and B. Terminals are found on the right side, where each symbol is replaced by a combination of terminals and non-terminals. Because there is not specific order for applying the rules, a single grammar may produce multiple derivations. By example, in this case, we apply rules 1, 4, and 5, respectively. By applying rules 2 and 3, we obtain this other sentence, but were obtained from the same grammar. Similar to when a regular expression derives into multiple options, this will be the same. Now we can produce anything within these production rules. For example, this derivation leads to this expression. Infinite combinations. You will be asked to scientifically express the language of a grammar, and according to the set of productions, grammars are classified as follows. Regular grammars exist through FSA. In addition to detecting regular expressions, it can also detect formats. That is, we don't want users entering non-valid information. The first rule only allows numbers and letters. The second rule allows the system to automatically add those symbols. The non-terminals used are listed along with the production rules, so that this construct only generates valid email addresses. Let's discuss context. Consider a simple calculator for obtaining the result of an arithmetic operation between two integers. This context-free grammar will solve problems like within a function call. Remember this word function. For example, if we want to include negative numbers, we might need a prior transposition operation, a function call. The term dependency can describe a more advanced chain process, such as a professional calculator. We are now solving complex problems like and allowing negative numbers with conversion processes. A context-sensitive grammar is more appropriate for such a complexity. This allows for syntactical advantages such as restrictions that avoid divisions by zero. Finally, we have unrestricted grammars. They can be used to construct anything. A good example is a bit-handled machine. You will be asked to represent a simple grammar to produce something like 2030 in binary. First the terminals 1 and 0, then 11-bit string. We use the symbol A as a non-terminal and a rule to allow A to be double. In this way, this derivation produces 2030 with as few rules as possible. Like automata state diagrams, derivation trees are vehicles for visually expressing context-free grammars. For example, this derivation was depicted so that the terminals are visible as possible. In the next unit, we will expand our discussion of abstract machines. Thank you very much for watching this video and see you in the next unit.